science is saving us. It has been our bridge to progress, and it has inspired us to understand the universe from the atomic level up until the marvelous expansion of the galaxies. Clubes de Ciencia México is a non-for-profit organization founded in 2014 that shares cutting-edge scientific knowledge with Mexico's future scientists and innovators, creating an ecosystem of equity, curiosity, and critical thinking. Through an educational model of courses designed and delivered by experts from the most renowned institutions in the world, Clubes de Ciencia México inspires the new generations to follow and achieve their dreams. Connect to the future with Clubes. Get smart. Support the future minds. Donate now.
Hola, muy buenas tardes a todos y a todas. Bienvenidos y bienvenidas a nuestro tercer webinar del ciclo Conéctate al Futuro. Mi nombre es Ana Patricia Ruiz. Yo voy a estar moderando el webinar del día de hoy que nos va a hablar acerca de exoplanetas. El día de hoy, por cierto, Jake se disculpó con ustedes porque tuvo unos problemas de salud por los cuales no se pudo conectar, pero no por eso vamos a cancelar nuestra plática del día de hoy. El día de hoy, nuestro presentador es Alexi, que él tiene una maestría en astrofísica en la Universidad de Francia. Él es de Reunion Island, una isla que está por allá cerca de África. Y también es un candidato a doctorado por la Universidad de Southern Queensland. Entonces, Alexi, además de dedicarse a la ciencia, le encanta surfear, le encanta escalar. Y, pues bueno, también le gusta hacer ese tipo de actividades. Y, pues nada, lo tenemos el día de hoy aquí con nosotros. Hi, Alexi, how are you? Oh, I cannot hear you, sorry.
Oh, no, it's better?
Yeah, hi, how are you? Thank you so much for taking your time to come to give this presentation.
Yeah, no problem.
Yeah, okay. Okay, well, the public is all yours.
Okay. So hi, everyone. So I'm going to talk in behalf of Jake today. Unfortunately, he's not here. So Jake and I work together at the University of Southern Queensland here in Australia. And so without further ado, let's go. So are we alone? That's the big question behind exoplanet research. And we'll try to answer that today. Not answer it, but see what we can do about it. So our galaxy is quite big, hundreds of billion stars. And the question that we always have wondered is, are we alone out there? Like, is there planets that we can find that are like our own and that we can, and where there's life on it? In 1992, it was a very important year because Jake was born. So that's little Jake there, a bit more like, 30 years ago now. And also in 1992, what happened is that the first exoplanet was found. This exoplanet was orbiting a quite crazy star that we call a pulsar, which is a star that is rotating very, very fast, and it cannot suit life. But it was the first hint of planets, so it was showing that there are planets that exist out there around other stars, and because before that we thought our solar system was the only one. But this one, called PSR B1257+12, is, like its name, a bit boring because we want to find stuff more exciting around stars just like the sun. So these are the names of those first found planets. And after that, it just kept growing. We just kept finding more and more exoplanets. It was the start of a long journey that we're still going today. On this graph, you can see at the bottom the years since 19 1995 until now, we have found 4,375 exoplanets. This is a lot. This is a lot of planet, and we keep searching because the more we look for them, the more we find them. So this is really exciting stuff. But the first question is, so how do we find those exoplanets? So we have different methods, and the five common are those ones. So the one that I showed here are microlensing and direct imaging. These are just responsible for a very small amount of planets that we've found. And the most interesting one, or the one that are the most successful, are transit and radial velocity, which I will explain right now. So for those one that are not that successful because they're hard to put in place, we have microlensing, which goes something like this. So on the right, you can see the time and the light emitted by a star. And what you can see is when a planet passes in front of that light, due to general relativity, it bends the light. And we can actually measure this bend of light, but it's very subtle and it only works for planets. So when a star with a planet passes in front of another star, you can see there is a little extra dip here on the curve, and that's a sign of a planet. But this is really hard. You need a very good alignment of the stars, and it hasn't led to a whole lot of exoplanets. Then we have direct detection. This is the one that seems the more obvious. We just look at the star and we see the planets. Now this one is extremely difficult because the star is so much brighter than the planets surrounding it that you need to occult the star, mask it, and try in the residual to find traces of planets. These planets are very far from the center star and are very massive. So we mostly find big planets with this method, and just a few of them because it's really tough. Now the most successful is by far the transit method. So in the transit method, if this planet is aligned, it passes in front of the star, we actually see a dip of light in what we call the light curve in the graph you can see on the left. It's like the moon eclipsing the sun, exactly the same. And by studying the shape of this light curve, we can figure out the radius of the size of the planet. This very successful method has led, for example, to the discovery of the TRAPPIST-1 system. So TRAPPIST-1 is an extremely exciting system. It's been found in 2017. So you can see on the right the image, which is a bit boring, but when you actually look at a bit closer, you find what we have on the left, which is a star that hosts 7 planets. Now, this star is what we call a M dwarf, or a small star. So on the middle of the picture, you can see the representation of the system and the 7 planets. And you can see the size of the star compared with the size of the sun. As you can see, that star is much, much smaller. And what's very interesting is that you can fit all of this system under the orbit of Mercury. Like the outer planet, the planet H, would be much, much closer than relative to our sun than Mercury is. But of course, because the star is much smaller and its light, it's much dimmer, it means that some of these planets, we believe, are in the so-called habitable zone. So the habitable zone is a place where you don't get too much light, so you get burned, and you get enough light, so it's not a nice word, where we think life could potentially evolve. Of course, we haven't found any sign of life on those ones. They are a bit too big to host life, probably, but this system is very, very interesting. And on top, you can also see at the same scale the orbit of Jupiter's moon, which are comparable to the size of the system. So very compact system, but very interesting. This is Kepler, the space telescope that has helped us for the last, I think, 10 years to find all these exoplanets, a lot of exoplanets with the transit method. It died well, it was decommissioned last year or 2 years ago. And it has a bit of a funny story because as you can see on this image, you have the Kepler field on the top left, or on the left of the image. This is the original part of the sky that Kepler was scrutinizing. So it was looking at it for a very long time, and then looking for as I showed before, dips in the light of the light curves as signs of exoplanets. But then one of its wheel that controls the pointing of the telescope broke, and the engineer really smartly found a way to make it point somewhere else while it was drifting, and they could observe all these sectors that you can see numbered 1 to 16 there. And it was really the beginning of the era of massive exoplanet finding. We found a few thousand thanks to Kepler. Then arrived TESS in 2018. It's still going. TESS is the successor of Kepler, is an amazing space telescope. And it has 4 cameras that observe a chunk of the sky each month. So it stays on the part of the sky for 1 month and then go to another one and then beam the data back to Earth. And here we analyze it and try to find planet in all this data. And this is the part of the sky that TESS covers. It's huge, it's pretty much everything. And that was his first intention, to cover all of this. And actually next year it's gonna continue his mission, which was not planned, and fill the blank, or fill the dark areas there. And we'll hopefully find new planets there as well. So next we have the Radial velocity emitter. This is the one we work with at USQ. This is the second most successful one, and it works something like this. So in this image, you can see the planet orbiting the star. And because of the action-reaction effect, the planet actually pulls and tugs the star around a little bit. And when we look at the star, we see the wavelength of light being stretched and compressed because of this influence. This is called the Doppler effect, same as when you hear a ambulance passing in the street. The pitch will go from being low to high, and the planet, if it's close enough and massive enough, it's going to have a very, very tiny effect on the star. And this we can measure with our spectrograph that are precise enough. So spectrograph being the instrument we utilize to analyze the wavelength of light. And this is a spectrum of the sun. So you can see a lot of absorption, like ray, we call them, in black. And these are when the sunlight is absorbed by some element within the sun before it reaches us. And so how do we do with the previous method? Well, we look how those dark patches move over time, and this is a sign of a planet. So of course, this movement are very, very subtle, but it enables us to find planets and to actually find the mass of the planet. So remember I said that with the transit, we can find the radius of the planet. And with this method, which is complementary, we can find the mass of the planet. So TESS looks out for a planet with the transit method and find their size. And here on Earth, we, with the radial velocity method, we find the mass. And we do this here at USQ with our observatory, which is called the Mount Kent Observatory. We work with a lot of different universities around the world, and that's our job here. We wait for TESS to tell us, oh, there is a planet there. We found a planet of this size. And then what we do is we look at that star and try to follow it with the radial velocity method and find its mass. So we are located in Australia. You can see on the right in Queensland, there is Brisbane. And if I zoom in on Brisbane, we can see the Mount Kent Observatory, which is an hour south of Toowoomba, where our campus is located. So this is a picture of the sky above the observatory. It was taken in May last year. It looks beautiful, but here the definition is a bit, it's not the best, but it does look beautiful, and we have a beautiful sky, which enables us to characterize this planet. And we even have some visitors sometimes. So this is a camera that looks at the domes that you can see behind. Each one hosts one of our telescopes. We have 4 telescopes that work together. And yeah, we have the visit of some little Australian kangaroos sometimes. They like the warmth of the infrared camera. So there is another instrument called Veloce, which has been commissioned 2 or 3 years ago. It's another spectrograph for looking for the mass of some planets. And this one is attached to the very large AAT telescope, which is 4 meters in diameter. And it's located in New South Wales, south of us here. This is the largest optical telescope in Australia. And Veloce promised to offer very good science and to find smaller planets. So the larger the telescope, the fainter the stars you can see. And then the better the spectrograph, such as Veloce, then the smaller planets you can find. So this is Jake. He's in the observing room that we have at USQ. This is our remote observing room for observing with Veloce that you just saw before. And now that we do this work of finding the mass of the planet, we have 2 very important things. We have the radius and the mass of the planet. And once we have those 2 components, we can derive the density of the planets. And what we've noticed is that planets come in many different flavors. We have the Earth-like planets, and this distribution is what we think is, based on what we found so far, it's what we think how common each of these words are. So these are the Earth-like planets that we are really hunting for. Then we have the hot Jupiters, the Jupiter-like planets. So these ones are just like Jupiter, meaning they are gas giants made of gas rather than rock like Earth, and they orbit quite far from the star. And then we have the hot Jupiters that are Jupiter that orbit very close to their star, and they are very, very hot and also very interesting. Then we have the Neptune and super Neptunes. So we call them Jupiter and Neptunes because they have the characteristics of Jupiter and Neptune, which is what we know in our solar system, and that is the closest to that. So this one are a little bit smaller than Jupiter-like planets, but they're very, very common. And they're also the easiest to find. And then we have super Earth, and super Earth are also very common. Super Earth are Earth-like planets, which mean rocky, but more massive. So from 2, 3, 5 Earth masses. And yeah, these words come in different flavors. Some are very, very close to the star, and so they are very hot. We have magma word. We have word with very high clouds like Venus. We have probably ice words that are very far. And we now only start to know what those words are made of. And to do this, we use new techniques to actually analyze the atmospheric composition of these planets. And we can do that for some of them. And they reveal very interesting things. And that's in the way of finding life, because if you find some components that are very, or that we think are very only generated by life forms, then it could be a good indication of life elsewhere. And so Jake has participated in some of these discoveries and some of these characterizations. This is HD 76920b. It's 600 light years away, the star, and this planet has a 1.1 Jupiter radius. Sorry, so it's a Jupiter-like planet, and orbits its star in 400 days. It's also a very eccentric planet. as you can see, this is the scale, put to scale with the solar system, and it's like an asteroid, we would imagine it is, because it comes very close to the star and it goes very far away, so it's a very peculiar planet. It's typically not the kind of planet we would be imagined as habitable. And oh yes, the names are really nice. So the names for the planets are the name of the star, and then B if it's the first planet found, and then C if it's the second planet. It's not very sexy, but otherwise we would be confused with so many different names. So this planet is very eccentric, and of course that's not what we look for life, because it's sometimes very close and then very hot, and sometimes very far and so freezing. So HR 858, that's another very interesting system with massive planets that are around 15 Earth masses and that orbit from 3 to 11 days, the star. So 3 days is very, orbiting in 3 days means that their year, which is for us 1 year, of course, is only 3 days. So they orbit extremely close from the star, and are also very, very hot. They get a lot of light. This one is very exciting. From June 2020, you can see Jake's name here. This is a Nature paper and has made a lot of noise in the community. This star is called Eumic, and it's a very specific star because it's very, very young. It's a, I believe, 2 million year old star, so the sun is 4.5 billion years old. So 2 million is really a baby infant star. And we struggle to find planets around these stars. But this is very important because if we find planet around very, very young stars, we can know how quick they form, how they form, and there's a lot of exciting science there. So this was a big discovery last year that we contributed with our observatory. And this is, as you can see, there are many authors. This is an international collaboration. And this is what we imagined it could look like. We can't see very well on that picture, but the dust there is due to the young, because the star is very, very young, there is a disk around it as it just formed, and that's where the planets are forming. So in the case of Eumic, those planets were seen within the disk. Very interesting science. So the future of exoplanets. So TESS has not retired yet, and we'll see plenty of new exoplanet in the coming future. These are some predictions of what we think we will discover. You can see the number of detection there. You see that the number of giant planets go up to 17K. This is based on simulations. Because of what we found, we can expect the true number of planets to be something and try to actually keep looking for them and find them. And this is a plot showing how we think every year what's going to happen, how many more planets we will find. So different colors are different methods. And of course, what's the most interesting are the lowest dots on this graph, because the vertical axis is the mass, and we want something that are close to 1 Earth's mass is. So we can see that this plot year after year is going to be filled with planets smaller and smaller, because our instruments get better and because our techniques are also getting better. So we can hope to find smaller and Earth-like planets. This is the James Webb Space Telescope. This is the future of exoplanet characterization. This space telescope is going to replace Hubble, if some of you are familiar with it. It's a gigantic space telescope. Its only drawback is that it's been pushed back for many years because it was really, really expensive, and it should have launched for already 5 years, but it's still on Earth. It should launch this year, hopefully. And this is going to enable to discover so many new planets and smaller planets. And also, it's going to be doing atmosphere characterization. So when is it going to be ready? I don't know. I think that the launch is due this year at some point, so keep posted. But it's been the 5th time we're waiting for that, and it's been delayed, so we never know. But hopefully this year or next year. Yeah, this is Jake next to the, I'm not sure where he was there, probably conference, the TESS conference, I believe, next to the James Webb Space Telescope logo. And so, yeah, so as we saw, there are a lot of exoplanets out there, more than 4,000 that we found. And there is still a bright future, and new instruments are coming. We're going to find more and more planets. And we realized a few things. The first one is that there are other worlds out there, and we are really excited to see this unfold, and now we're going to find life and everything. But another thing that struck scientists and that struck us is that yet we haven't found something like Earth. And even though if we would find one, it would be too far to go, and it would be in such a distant future that one of the conclusions that we have is what we keep searching is that there is no planet B, right? We really have to take care of this one because we haven't yet found another one like that. And even if we would, it would be really hard to go. So thank you for listening to that presentation. I leave you with this, and I strongly encourage you to follow Jake on his social media and have a look at his website, jake-clark.github.io. It's very well made. And thank you. If you have any questions, I'll be happy to answer them. Oh, I think we can't hear you. You're muted.
Okay, great. Yeah, well, thank you very much. It was a really, really good presentation. Also, given the time that we gave you to prepare. There's still some questions. So the first question is, and of course, these questions mostly goes to what you were just discussing at the end, which is about finding life. So the first question is, what's the best prospect of Earth-like planet that you have found?
So there are a few. I wouldn't be able to give you the names of those planets, but there are a few. So the thing is, every time we find a planet which is on the scale of the Earth mass, it makes the news. And every time is, oh, we found a new Earth, we found a new Earth. But we haven't found anything that is just like the Earth yet. It's either always a bit too big, or it's a bit too far, or so there might be a few, maybe 2 or 3 candidates that could be, but this is still the very beginning of finding planets that are very much like our own.
Okay, so the next question is more about the nature of these planets. It's, can you obtain information about the conditions of these exoplanets? And if so, what is the information that you can get or retrieve?
So the thing we start to do now, and as I showed, the James Webb Space Telescope is going to be an advocate for that, is to probe the atmospheres of those planets. So if you remember the transit method, where the planet passes in front of the star, we can actually look at the change in the elements we see in the light, or in the traces of elements, of components, chemical components. And this can be indication that this is happening in the atmosphere of the planet. The problem is that if we need extreme sensitivity, and we're just starting to find. But we're starting to find water vapor, a lot of, it was on Venus, but someone claimed they find phosphine on Venus. And so we can start to look at, Venus is close, so it's easier. But for exoplanets, we can start to look at atmospheric components, yes.
Okay, thank you. The next question is, what's the chance that there's life in other planets?
I wish I could give a number, but I don't know what exactly are the chances. There's a lot of questions now. We are wondering so first we need to define what life is, and this is already very hard because some people have come saying, oh, maybe there are forms of life that are not made out of carbon like us, but maybe out of silicon or things like that. So we first need to define what life is, and then now life as we know it, we're still not sure what it needs. So we look for planets that are in the habitable zone, which is a place where liquid water could survive, because we think that's essential. But there are probably many other factors that we are still trying to understand.
Okay, the next question I think is really good, and I think it's a little bit related with your research. It's, does this help learning about the formation of planets?
Yes. Yes, very good question indeed. So, for example, Eumic, which was a really young planet, helped us doing just this, because if we find planets at different stage of the star life, so if they are very young, a bit less young, etc., we can see how they evolve. For example, the hot Jupiters, which are the very warm Jupiters that are very close, we think that they start their life very far and then they come in close to the star. So if we can find stars that show this process, so planets in a different stage of their life, we can infer what's happening. Yes, it's possible.
Okay, thank you. The other one is more technical, the next question. So if you will classify the telescopes we have, how many times we have to visualize these exoplanets?
So how many types of different telescopes? Is that
Yes.
the question?
And which are these types, of course?
So what I talked about today is more optical telescopes, so looking at visible light. We can look at other signs in the infrared, and of course this requires different technologies. But more than the telescope, the instrument is important. So we have telescopes of very different size. We have in Chile, there are very big telescopes that can look at fainter stars and get more light. So the size of the telescope may be very important. And also, yeah, the instrument we attach to it that enables us to do different things with the light we get from the telescope itself.
Okay, thank you. Another question, going back to life. So if we find another planet with the same components that we have on Earth, do you think it will be possible to inhabit it?
So the first thing is that we would need to go there, right? So I don't know if that's part of the question, but that's probably the biggest problem. We are trying to figure out how to go to Mars already, which is next door. And Mars is actually a very good example because we think it used to be like the Earth and might actually was habitable a long time ago. But as human, we are really we adapt very well to environment, but we are very limited. If the temperature drops below 0, we need clothes. If we go above 40, we can't stay. So the range at which we can habit in our normal condition is very, very small, and that's why we think it's going to be very hard to find a place that we can go without, suits or anything. Or
Yeah, I think it was really important what you said at the end, that we only have one Earth so far. So we should keep, taking care of it. I think this is our last question. What elements are needed to classify the planet into an exoplanet?
Okay, good question. I might not have made that clear. So exoplanet simply means planet outside the solar system. So everything that's the 8 planets we know in the solar system are planets, and all the others are exoplanets.
For example, what will be the difference between an exoplanet and an asteroid that it's kind of
okay. So so there are different bodies in space, right? So there are stars, which are the biggest, and stars have an internal mechanism that makes them emit light. And planets are the next largest thing, which is inert. It's not emitting anything, invisible light at least. And then you have smaller bodies that are asteroids. And the limit is somewhat hard to draw. For example, Pluto was a planet before, and now it's not one anymore, because it has to have a very, there is a mass and size threshold above which you're a planet and under which you're not. So it's just a matter of definition.
Okay.
Yeah.
There's one last question. You don't have to answer if you don't want to. But it's, what do you think about Elon Musk and his plan to colonize Mars?
Well, we don't know if he's going to succeed, right? But that doesn't seem too unrealistic for him to succeed. But so my personal point of view on it is that it's great because we want to go and see other planets and everything. But also, as I said, like Mars is never going to be like Earth. So if we just focus on going to Mars and don't focus on us here and what's going to happen to us here, it might be a problem. But of course, it's very exciting as well as in going to other planets and so on. So.
Okay, great. So these are all the questions that we have for today. Thank you so much. I think
No problem.
really nice webinar. Do you have anything else to say to finish and to close the presentation?
No, just the last thing is go to Jake's website or to our USP website and see what science we're doing, and hopefully this inspires people to do astrophysics research.
Okay, thank you. Great. Okay, have a nice evening.
Thank
Bye.
you.
Bueno, pues muchas gracias a todos por conectarse el día de hoy. Creo que sí fue muy importante saber que todavía no encontramos un planeta al que nos podamos ir mañana. Y de hecho, a eso viene nuestra plática, un poco orientada a la sostenibilidad de la siguiente semana, que es acerca de los datos de la actividad del transporte, y va a ser un enfoque mexicano, así que esperamos que se puedan conectar. Otro anuncio que también me gustaría dar el día de hoy es que el próximo 14 de abril nuestras donaciones se van a duplicar, así que por favor, si quieren apoyar a Clubes de Ciencia, pueden hacerlo este día, ya que vamos a recibir el doble de las donaciones. Bueno, pues esto es todo por hoy. Les agradezco mucho que se hayan conectado. También, sí, apóyennos, donate to Clubes. Y bueno, pues nos estamos viendo la próxima semana a la misma hora. Y bueno, pues gracias.
clubesdeciencia.mx